Hello everyone, this is Ketish here. In this video, I'm going to go through the 2023 Combined Science Physics Paper 2 Foundation Tier. Question number 3 is on the topic of magnetism and electromagnetism. Figure 4 shows iron filings sprinkled around a bar magnet. This is a practical that you would have done either in the class or seen it as a demonstration. So you can see there's a bar magnet in the middle surrounded by iron filings. Now they haven't shown you the poles of the magnet, which is the North Pole and the South Pole, which doesn't matter for this question. So why are the iron filings attracted to the bar magnet? Right? Now, why would iron filings be attracted to the bar magnet? Right? Iron is a metal. Well, if you use aluminium, it's not going to be attracted to the bar magnet. Like copper, gold, aluminium, lead, none of the other metals would actually attract. It's a couple of metals that is going to be attracted, mainly iron. You could say steel, cobalt, and nickel. These are the only 4 metals that are going to be attracted to the bar magnet. So iron is charged? No. Iron is heavy. Iron is magnetic. Question 3.2. Figure 5 shows a bar magnet. Draw magnetic field lines to show the magnetic field pattern around the bar magnet. You should add arrows to the field lines to show the direction of the magnetic field lines. So you're going to get 1 mark for drawing the magnetic field lines, and you're going to get another mark for adding the arrows to show the direction of the magnetic field correctly. Hence the 2 marks. So how do we start here? Here they have given you a bar magnet, rectangular shaped bar magnet. So first of all, you would actually draw 2 straight lines on both sides to show that the line in the middle is actually going in a straight line. Then you would draw 2 curved lines on both sides. Doesn't have to be perfect. Right? And then you draw 1 line on the top going from the North Pole to the South Pole. And you need to make sure that, let me redraw that line. Right? The lines are not actually crossing each other. So again, as you can see, my lines are not perfect, but that's fine as long as they're not crossing each other. Now, these lines should give you 1 mark. You should draw a minimum of 3 lines on both sides, both ends of the pole, and 1 on the top and 1 at the bottom. The direction is always from north to south. So north to south means it's going away from the north. So you would add the arrowheads on the lines, not at the end over here. You would add it in the middle of the line. So this line is actually going from the north to the south. So they're both pointing towards the south, and these lines are pointing towards the south as well. Figure 6 shows 2 bar magnets. So you have 2 bar magnets, X and Y poles. They haven't given you the poles. The magnets attract each other. What conclusion can be made about the 2 poles marked X and Y? They are both north poles? No. If they are both south poles? No. They are opposite poles? Yes. If they are both like poles, like North Pole and South Pole, these 2 will repel, not attract. Figure 7 shows some plotting compasses around a wire. There is no current in the wire. So here you can see the switch is not closed, so there is no current. The plotting compasses are all pointing in this direction up. The question is asking 3.4, why do the plotting compasses all point in the same direction? Well, they are not pointing or responding to anything that's happening in the circuit. They're all pointing to the Earth's magnetic North Pole, or they are aligning to the Earth's magnetic field. So they are aligning to the Earth's magnetic field. Or you could say they are pointing to the Earth's North Pole. That's what plotting compasses do. They always point to the Earth's North Pole. When the switch is closed, there is a current in the circuit, in the wire. The current creates a magnetic field. What shape are the magnetic field lines around the wire? Now, when there is a current around the wire, the magnetic field lines are circular in shape. So, if you have the wire like this, then you're going to have circular lines. Magnetic field lines are all around it. So, you'll have them as circular field lines like that. And the lines are actually much closer together near the center. As you move further away, the lines actually spread out because it's getting weaker. Next part, a student investigated the force exerted by an electromagnet on a paperclip. The student varied the distance between the paperclip and the electromagnet. Figure 8 shows the equipment used. So here you have a Newton meter which is measuring the force, the pulling force, and the Newton meter is attached to a paperclip, and that paperclip is being pulled in this direction by this electromagnet. When you switch it on, this becomes a magnet and pulls the paperclip downwards. And as you can see that it's actually reading a certain value on the Newton meter. So the student recorded the reading on the Newton meter for several different distances. The current in the electromagnet was the same for each distance. Complete the sentence. Choose the answer from the box. In the investigation, the current was what type of variable? Now, we are saying the current in the electromagnet was the same. If you're going to keep that the same, it should be a control variable. Control variable. Now, the dependent variable is actually the force here because it depends on the distance. The independent variable is the distance between the paperclip and the electromagnet because they're changing. They're recording the reading on the Newton meter for several different distances. They're changing the distance on purpose. That is our independent variable. Write down the size of the downward force on the paperclip in figure 8. So what is the force recorded? So let me zoom that in a little bit. And that reads, right, that's 3. This is 3.5 over here, and that's one line after 3.5. So that should be 3.6 newtons. Let's zoom back in. That's 3.6 Newton. The distance between the paperclip and the electromagnet is increased. What happens to the size of the downward force? Now, if you increase the distance between the paperclip and the electromagnet, it's not going to get attracted that much. So the force would go down, or you could say the force size would decrease. That brings us to the end of question number 3, and I will see you in question number 4.